Today I'm going to introduce our work, NDN in large LEO satellite constellations, a case of consumer mobility support. Large LEO satellite constellations, they intend to provide low latency and high bandwidth connectivities. To provide low latency, satellites are launched at low altitudes, for example, 340 miles. At low latitudes, they are moving fast, resulting in a handover every 2 to 5 minutes. Also, they require a massive number of satellites to provide continuous connectivity. In terms of hardware resources, traditionally they are considered to carry limited amount of resources. In June 2020, SpaceX disclosed that each launch carries 60 satellites containing 4,000 Linux computers. So this information demonstrates that it is able to carry general purpose operating systems, which means we can run some programs over there. We take a further step to hypothesis that there can be a certain amount of computing and storage resources. At least they may be able to run, to equip those resources, which is a foundation to run NDN or more complex services. In terms of connectivity, there are two stages. For stage 1, there's no dedicated inter-satellite links. So each satellite serves independently, and ground users connect to one satellite, which connects to the ground stations. So just one hop to provide internet connectivity. For stage 2, which is also our study in this paper, we inter-satellite links. And one common design is there will be 4. There could be more, but in our paper, we assume there are 4 inter-satellite links. Also uplink and downlink. So each satellite has 6 links. For inter-satellite links, 2 are on the same plane, so orbital plane, so they are relatively static to each other. And 2 are on different orbital planes, so they may change over time. Okay, after a brief introduction, next, the very first questions we ask is why NDN? Why it is suitable in this scenario? We list several architectural benefits that could be potentially suitable for this scenario. The first one is adaptive forwarding. As we mentioned, this scenario, when we form a networking, there will be multiple paths. Because each satellite has 6 links, so for 2 endpoints, there are multiple paths, which means there are multiple forwarding choices. For uplink downlink, they can use both radio frequency and optical communication technologies. The optical communication technologies, it provides much higher capacity, but it suffers from weather conditions. For example, it can be blocked by cloud coverage, which is unpredictable. For inter-orbital optical links, they change over time, and from the network perspective, it takes non-trivial time to set up. So this brings challenges in routing protocols. And we think NDN's adaptive forwarding may play a better role in this scenario. The second point is in-network caching. In NDN, it caches interest, which provides built-in multicast that can reduce network traffic. In-network data caching can also reduce both delay and network traffic. Compared to terrestrial networks, bandwidth is still a valuable resource in LEO satellite constellations. The next one is off-the-grid communication. An example is in remote areas, users can use the satellite's local area network connectivity to communicate with each other. This is the off-the-grid communication. And the NDN provides a unified data retrieval protocol, no matter it is on or off the grid. In IP network, to support off-the-grid communication, it requires ad hoc mechanisms. Most of today's applications, they require a predefined server, the cloud server to be working. Okay, next is data mule services. This service is especially useful for stage 1 constellations because there's no inter-satellite connectivity. When satellites move into remote areas, they can collect some data, and when they fly in back over the ground stations, they can send the data to the ground stations. This store and forward capability can be easily supported in NDN. Similar argument as the previous one, NDN provides a unified retrieval protocol, data retrieval protocol, no matter it is data mule service or it is off-the-grid communication. The next one is in-network and edge computing. Karen Selins has, I discussed this with Karen Selins, when this will be useful. And she mentioned there can be climate satellites and there can be telescopes in the space. There are several of them and they collect data in a distributed way, massive data. And if there are satellites, LEO satellites, they can utilize LEO satellites to do the data delivery. And if the LEO satellites can provide in-network computing, it can improve the delivery's efficiency. For example, they can remove the duplicate data. They can have more complex algorithms in the middle. So it is useful if we have such infrastructure. And there are other papers, they argue that NDN can reduce the complexity of such infrastructure. The next one is consumer mobility support. We will elaborate it in the following context. So last one is data-centric security. This is the foundation for all the features we just mentioned. Okay, so consumer mobility support. NDN provides native consumer mobility support. That means because NDN has poor communication model, applications can simply retransmit interest after timeouts, and this deals with handovers naturally. The side is that interest timeout in applications can be too long to negatively impact users' quality of experience. Also, they may have negative impact on congestion controls because they use timeouts as signals. A better solution is in-network interest retransmission, which means when the end node it detects a handover, it connects to a new satellite. It can retransmit pending interest to the newly connected satellites. So there is no need to wait applications to take actions. Can we do better than this? The performance of this depends on if retransmitted interests are forwarded to the previously connected satellites or forwarded to a new satellite. Which means if they use the previous path, the efforts of previous send interests can be utilized. The data may be retrieved back on the previous satellites already, so there is a cache hit. Then the next question is, does the routing paths overlap for LEO satellites because they're moving fast? We did a simple simulation to simulate the Starlink constellation, and we picked 2 cities, and we find that the routing paths do not overlap in this case. For example, the red routing path and the green routing path are 2 different routing paths before and after the handover. And we can see they use different satellites. So we make an analysis and find that if we use interorbital planes satellites for the routing, they will use different routing paths. If we use the satellites on the same orbital planes, they may overlap. So it is more like, because for 2 cities or for 2 geolocations, the routing path may not be always be on the same orbital plane. So it is more likely we have the first situation. So our idea is, can we change the case? Our idea is straightforward. We can direct forwarding using a hint. So we can redirect the routing path 2 to the routing path 1. And this mechanism is actually supported in NDN via forwarding hint. So here is a concrete example how we use forwarding hint to do the direct routing, the forwarding. For example, when we send the interest, there is a field called forwarding hint in the interest. And when we send the retransmit interest, we can add the name of the previous connected satellite to the forwarding hint. So those interests will be forwarded to the previously connected satellites. And those then will be find its own way. So this mechanism requires the usage of forwarding hint, and also it requires the satellites to have a unique name. Okay, now come to evaluation. Our goal is to evaluate the performance of the 3 mentioned mechanisms, which are application interest retransmission, in-network interest retransmission, and in-network interest retransmission plus forwarding hint. The metrics we use are the average data retrieval delay, the number of the retrieved data, and also effective data retrieval. The scenario is one consumer in one city downloads from a file that is generated by a producer at a different geolocation. And we collect data in a period of 2 seconds, one before the handover and one after the handover. So just to note that this period, if it's longer, the difference will be smaller because the number of traffic affected by the handover is just is a small portion if we take a longer time. So if we take a smaller time period, the difference will be bigger. Okay, the first one is the average data retrieval delay. We pick 3 cities, Beijing, New York, Sao Paulo, and each of them plays as the consumer and producer. And we can see here is the average data delay, the naive one or the native one, it has a much higher delay than in-network retransmission, also with the forwarding. The second one is the number of retrieved data. So we can see that during the handover period, both the in-network retransmission and the forwarding one can retrieve more number of data than the native mechanism. So the last one is effective data retrieval ratio. We can see if we have forwarding hint, the previous 2 metrics with or without forwarding hint, they are similar. But in this case, we want to demonstrate that with forwarding hint, the effective data retrieval ratio is higher, which means the number of data wasted on the path is lower, because for in-network interest retransmission, if it takes a different path, there will be some data delivery using the previous path wasted because they are not retrieved back and they're using a new path. So there will be traffic wasted, which consumes the resources, bandwidth resources. So this is all about work. Thank you for watching.